Okay, let's continue our discussion on development length or length of development. So, for the length of development that we have derived on the previous video here, okay, so remember that this is our basic formula, LD, okay. So we are going to consider now the flexural bond concept, or simply the development length or length of development concept intention. Okay, okay, intention. So we're considering steel bars intention. Okay, so these are for steel bars intention. So if I have here a slice of a beam dx, okay, assuming that I have a whole beam here, and then I just get a slice of this, okay, dx. So this is my slice of the beam. So I get this one here. So this is the slice. And take note that we already know that for strength design concept, we have what you call the witness stress block, okay, and the tension. Of course, this is on the left of the slice of the differential slice. This is on the right of the differential slice. So you take note that the stresses will be having some what you call this, the change, okay, because you are referring to a two point of sectional uh, lines along the beam. So this is section 1 and this is section 2, okay. So if I have two sections, definitely my compression force and tension forces will not be the same. This is C1, C2, T1, T2, or you can call it a C plus DC. Okay, there's a differential increment. Okay, and so with T plus DT. Okay, so if we take summation of forces along the horizontal, still the same, no? U times the summation of O dx. The only difference from the first derivation is that we consider only one bar del. Here we consider a summation of multiple bars. Okay, so this means that you are considering more than one bar. Okay, and that is basically the normal situation in the field. So summation of the perimeter times dx, no longer the length but dx, multiplied by the stress is the force. The force that will what? Tend to pull out, okay, this bar. So this is now the force that will tend to pull the bar outside, okay. So this is the force that will prevent rather the pull out, while the force that will pull the bar outside is simply these two here, no? T plus dt minus T, because that's going the left. So the differential force now will be the dt, okay? So this is the force that will prevent the pull out, and this is the force that will pull it out. They must be equal. That will pull the bars out. Okay. Okay, so summation O is the sum of the bar perimeter. And we take note that we also have an MM plus DM here. And if we are considering only this one here, and if I consider this moment arm to be JD, as we are using this parameter in our stress design, so JD is simply equal, or sorry, M is simply equal to TJD. And if I differentiate in with respect to dt, so this becomes dm is equal to dtjd. Okay, so we now have a term dt that can be substituted in this term here. But first, we look into what is TB. Okay, your tension at the bar is simply equivalent. This is for one bar. Okay, is simply equivalent to ASI over summation ASI. So what does it mean? It simply means that uh, if we divide one bar to its total and multiply it by T, then we get the tension in one bar. Okay? So this is just A over summation of A times T, or simply we can remove the summation. We can say ASI over AS times T. Okay, if we consider now one bar, we simply remove the summation there and place an ASI over AS here, dt. Okay, and then we can now make use of the same. U pi dB dx, this is the perimeter, okay, O. And then we have the area of one bar times dt is equal to 0. Or the area of one bar is pi dB squared over 4 divided by the total AS times dmjd. So where did this come from? It came from here. Okay. Sorry, class. Okay, it came from here. Okay, dt is dm over jd. Okay, so this is now your dt there. Okay, and some manipulations further will give you now u is equal to dm over dx. If I put it on the other side, dm is over dx, and then I divide the pi dB squared over pi dB. So what remains is dB. Okay, so I just cancel pi dB there and pi dB here. So I get 1 there. So this is now dB. Okay, divided by 4, that's 4 AS JD. Okay, so we have now the complete parameters on the right side. So what is dm over dx? So in your strength of materials, you just recall that this is the strength of materials, that dm over dx is equal to the shear. Okay, that's why your dm dx here becomes v db 4as jd. Okay, and we can drop actually the jd there and create a much simpler formula in terms of it was not simplified here, but jd sometimes are uh, assumed to be equivalent to D. Anyway, this is not yet the final formula. We'll check on that later. So that is for tension. So this is for tension. So for compression reinforcement, it's all about the same, no? Only this time we add a compression bar there to indicate C2. Okay, so C1 uh, is for the concrete in compression, and C2 is for the steel in compression. So we are now deriving the development length formula for steel in compression. So the formula is just the same. Okay, UODX minus ASI AS. So we're referring now to your steel in compression times, instead of having a DT, we have a DC2 here. And of course, same manipulation, but take note that our moment arm is no longer JD, but rather the moment arm from the compression to the tension is actually D minus D double prime. Actually, this is a double prime. Okay, assume. Okay, assuming D prime is equal to D double prime. So you get a D prime there. Okay, so this can be simplified further to a D minus D prime. Okay, so manipulation again will yield pi dB squared over 4 for 1 bar, AS for the total, O is pi dB, DC2 is dm2 over D minus D prime. How did we come about that? Because your M2 is simply equal to C2D minus D prime. So if I take the derivative of dm2, so this becomes dc2 D minus D prime. Okay, so dm2 now becomes, or dc2 now becomes dm2 over D minus D prime. Or if we take a look at this class, your 1 over D prime, or sorry, your D minus D prime can actually be uh, assumed to be alpha. Okay, okay. So your alpha is a fraction of the moment resisted by AS, so that your DC2 now becomes alpha dm2 over, or sorry, dm all over D minus D prime. Okay, so that's why there's a switch here, okay, of dm2 to alpha dm. So that is just uh, the difference between the derivation of the tension and the compression bar. And if you will take a look at the formula above, on the tension, the only difference is this alpha, and this is JD. Okay, so take note, for tension, it's U is becomes VDB over 4 AS JD. Okay, here it's an alpha B dB over 4 AS prime instead of S, and then your D minus D prime is JD. Okay, so this is for tension, and this is for compression. Okay, so the flexural bond stress in the compression is really high because of the end bearing resistance. So it means to say that the result of the test, the actual test, gives you higher uh, value um, that is given to the fact that there is an end bearing resistance. So what is an end bearing resistance? So if I have a concrete here, class, and I have here your reinforcement. Okay, if I push this reinforcement here, compression, so this end, excuse me, this end will actually be resisted by an end bearing of the concrete. So the concrete particles here, class, will have what you call an end bearing resistance. Therefore, your uh, bond stress is relatively higher than is computed on this basis. Okay, so the actual distribution of the bond stress U affected by cracking at flexural cracks is zero, and it's given by this figure here. Okay, so it's given by this figure here. So if you look at the cracks, if I have two cracks here consecutive, automatic your bond stress will be zero there because there's no concrete attached to that reinforcement. And surprisingly, the midpoint, okay, the point which is halfway these two cracks is again zero. So this now gives you an alternate sinusoidal effect on the bond stress. So it's just like a sinusoid or a sine wave that is actually, although it's not a sine a graph, it's actually an irregular graph, but it looks like a sinusoid that will create a pattern on how the cracks will be. So the more the cracks, if I have three cracks here, so my sinusoids will appear like this, no? 0, 0, 0, 0, and 0. So my wave will be smaller, okay? So I have a smaller wave, sorry, I have a smaller wave like this, okay? Okay, so something like this. Okay, so if I have cracks here, and of course my value of your bond or the bond stress will be smaller, smaller and smaller until such time that if I have too many cracks, like I have cracks there, cracks here, here and here, so my bond stress will be so small that this will actually be zero there, okay, zero, okay, until such time that this is very, very small. Okay, so this is small and very small until it reaches a value of 0. Okay, so that explains the two formula we need to remember if we want to get the length of development or the flexural bond stresses for tension and compression. Okay, so in the next video, we will be discussing some of the nature of bond failure. For the meantime, I'll be entertaining questions on this video uh, to clarify your concerns. Okay, so I'll see you on the next video.